Hey guys, Miss Rector here again. We're doing section 2 today from chapter 4. So, just sort of real short section this time. So we talked about light yesterday and all the things that we learned about light, how it has this duality, like a particle and a wave. So, more on that today. So, what was happening at the time? Scientists were puzzled why different range of wavelengths were giving us different temperatures. Like, why do barium and strontium give off different colors when you heat them? Why, when you pass electricity through a tube of neon, do you get this color and this red color? And, other gas mixtures can give you all these other colors. What's happening here? So, that's where there's three scientists we're going to talk about today: Planck, Compton, and Einstein, all sort of working on all these things. So for the Google form you're going to do after this, you really got to keep in mind which one of these people did what. Okay, so Planck, first guy. Planck's theory predicted how the spectrum of radiation emitted by an object changes with temperature. So if you look down here at this, I don't know, a sword maybe being forged, the heat, as you start to heat up this metal, it'll glow red and kind of orangey and then get like white hot. So Planck's like, why are these different temperatures different colors? What's going on here, right? And he proposed that there's a fundamental restriction of the amounts of energy that an object emits or absorbs, and he called these pieces of energy called quantum. So, what is this saying here? By the way, the plural form of quantum is quanta. So, think steps versus a ramp. So, when you've looked at a rainbow in the past, you probably thought, it was very continuous and one color just flowed into the other. What Planck is saying here is that it's not. There are discrete steps between one color and the next color and the next color. The steps are just so small that you perceive it to be continuous. So this is going to come into play when we talk about electrons jumping from one orbital to another and falling back down. They need specific amounts of energy. And Planck's saying that, these colors that we're seeing are associated with these specific amounts of energy. So he calls the steps of energy quanta. So here's Planck's equation. So E is the energy equals h nu. So h is Planck's constant. It's always the same. So 6.6261 times 10 to the negative 34th joules per second, I guess. And then we can use this equation to determine the temperatures of different planets. So if you've ever heard astronomers talk about like, oh yeah, that star is 14 light years away from here and it's this temperature, and you're like, how do they know what the temperature is? They're using this equation. The color of the light has a specific frequency. If you multiply it by Planck's equation, you get the energy or the temperature of that star. So we can use it to measure the temperature of things. Even though we can't feel the heat, we can see the light coming off of it. So we use that in astronomy a lot. Now, this is where we say, quantum mechanics makes people uncomfortable because you can't have separate rules for little things and big things. So it would be what quanta says is that, it would be if it was on our everyday scale, if the steps weren't so tiny. Think of like if you had a car that was quantized energy. That would, mean that, let's say the quanta steps were like 5 miles per hour. So you would go directly from 0 to 5 miles per hour. You could not go 1, 2, 3 miles per hour. From 0 to 1 or 0 to 5. Boom. And then you'd go from 5 to 10 and 10 to 15 and 15 to 20. So it would be this really jerky ride, right? But he says the steps are so small that we don't observe them in our everyday life. So if you think of a ramp, right? a ramp could have lots of little ridges on it that we as human beings perceive as just a ramp, but for a flea, that might seem like a step that they have to jump. So the quanta are so tiny that we don't notice them in our everyday lives. And that's where you're going to get a lot of this stuff to sort of bridge the gap between Newton's laws and these laws that we think of for tiny little quantum things. They're just so tiny we don't notice it. So Einstein comes along, and Einstein is the guy trying to explain stuff, right? He's the thinker, looking at the big picture, what is going on here. So there's this thing called the photoelectric effect, right? And let me go forward a slide here. What is the photoelectric effect? So when you shine some lights on certain metals, electrons get ejected. And we know from Newton's laws, force equals mass times acceleration. There has to be some sort of force, okay, if they're to make that electron move. And if you have a force, you need mass and acceleration. So what's if this light doesn't have any mass, what's going on here, right? So this is a problem. Why is light making a particle move? That would imply that there's some sort of force, like a particle in this light. So Einstein's trying to help explain this phenomena. And so if this is a strip of potassium and you hit it with light, if you hit it with like this wavelength of light, like a violet light, the electron moves off very quickly. If you hit it with a green, you get a lower velocity of the electron that's ejected. If you hit it with red light, nothing happens. The electron doesn't move. So you can think of like if you ever see the old movies where they're trying to develop film and they're in a dark room and they have a red light on. That's because red light has such low energy, it's not going to make the film, expose the film. Um, but if you flipped on the light and started getting the other parts of the spectrum in there, then that would ruin the film, right? So same thing happens if you have like a solar powered calculator. If you have your calculator handy, you see the little solar panel on it. If you were in a room with just red light, your calculator is probably not going to work. But if you have bright light at these higher frequencies, it'll eject those little electrons, so your calculator has electricity, right? So this is the photoelectric effect that Einstein's trying to explain here. So he sees Planck's idea, and he proposed that light quanta behave like particles of light, and he calls them photons. So when you think Einstein, think, he's explaining the photoelectric effect. He comes up with the term photon. Okay? When you think Planck, you can say, okay, he came up with Planck's constant on how to take the wavelength and predict the energy, and this idea of quantum of energy, right? Einstein, keyword photons, and he's explaining the photoelectric effect. Now, there's another guy, Compton. So Compton is actually doing experiments, right? Compton, when you think of him, think of like, oh, now he is testing stuff and doing experiments to demonstrate that a photon could collide with an electron. So he's sort of proving Einstein's idea here that a photon could collide with an electron just like two tiny little billiard balls might collide. And the photon is like a very special kind of particle that can travel at the speed of light and has a wavelength and frequencies, right? So he says light has the properties of both waves and particles. So these photons proposed by Einstein, Compton's showing that they do act like little particles. Um, so there's the duality of light. It doesn't have any mass, but it acts like a particle that does have mass. So I think that's it for this one. Yeah, tomorrow we'll get into a little more in depth on how this all applies to the atom and how Bohr took this and tried to explain the different light that you're going to see in atoms or when we heat things up. So we'll have a lab on this, the flame lab, um, for you to work on probably tomorrow. All right. Good luck. Answer those questions on section 4-2 about Einstein, Compton, and Planck. Have a good day.